Okay, so a real quick recap of where we left off just to get our mind back in the right space. So we looked at this image from Jay's tutorial that shows kind of the overall architecture of the transformer. And we learned that it's got 6 encoders, and the encoders all have identical architecture, but each has its own unique set of weights that it learns. So our input sentence travels through these 6 encoders, and then the outputs of that go into this stack of 6 decoders. And then that produces our final translated sentence. So that's the original transformer architecture, but we talked about the fact that for Bert, Bert actually just contains the encoder side. It doesn't include any of these decoder steps. And also, Bert has 12 encoders instead of 6. So with that, we are ready to talk about what's inside an encoder. So Jay describes it as having kind of 2 main layers inside of it. It's got a self-attention layer, and that's what we're going to be learning about right now. And then the results of the self-attention are fed into what he labels here a feed-forward neural network. So just kind of a standard multi-layer perceptron dense neural network layer. All right. So in order to keep us, in order to kind of reconcile what Jay is teaching us here about the transformer with what Bert uses, I'm going to try to reference the architecture of the Bert model as we go through Jay's tutorial. And in the sequence classification or sentence classification notebook, we saw that when we loaded the pre-trained Bert model with Hugging Face, that in this cell it prints out the full architecture of the model. It's this huge output window. And then we also saw that we could take the parameters out of the model and print out what they were and what their sizes were. So I did that for one of the transformer layers. So to kind of make sense of this, I put those 2 things side by side here and kind of color coded them by what they belong to. So let's take a look at some of that real quick here. So we start with an embedding layer here. So it's named embeddings, and it's got a number of different parameters in it. We've got the word embeddings, which have the following dimensions. So this is, 30,000 words in our vocabulary. And then 768 is the length of the embeddings. Kind of an unusual, number, 768. It's actually 512 plus 256. If that helps you to think about it. We'll see in the tutorial that the original transformer used embedding size of 512. So Bert is 50% longer than that. There's something here called position embeddings. We're going to have to come back to that. Jay addresses it later in the post. There's also something here that I believe is unique to Bert called token type embeddings. So another thing we'll have to come back to. And then we'll see this a few times in the model architecture, these layer norm layers. So layer normalization, the best definition I can give right now is that it's something that helps with training deep neural networks. So I'll have to learn a little bit more about the details of what layer normalization does and what specific problem it's addressing. So let's also look then over here at the architecture. So we kind of see the same things: word embeddings, position embeddings, token type embeddings. We see the class names here, Bert embeddings class. And we can also see that there's dropout added to the embedding layer. All right, so moving down, the next set of weights we've got here, they're all labeled self-attention. And we've got, there's some keywords here that we're gonna see in the tutorial real quick. Query, key, and value. For each of those, we have both a square weight matrix as well as a bias term. And we can scooch over here and look at the architecture. All right, so it's a Bert encoder. And a Bert encoder consists of a Bert attention layer. And this has 2 components to it. It has a Bert self-attention, and a Bert self-output. So here we've got the query key and value. And then for the self-output, it's just a dense neural network with layer normalization again. So we were just looking at the embeddings, self-attention, and attention output layers. There's two more pieces here. Zoom in a bit so we can see them better. There's this layer called intermediate, and it's just a dense layer, meaning like fully connected. And it's got a larger input dimension here. It's got 3,072 neurons, which happens to be 4 times 768. So we'll have to figure out what the significance of this layer is. And finally, there's this layer just named output. And it's another dense layer, scales things back down to 768, it has just 768 neurons. And those are all the pieces. So let's see if we can kind of figure out where each of these comes into play in Jay's tutorial. Okay. All right, back to the high-level picture. We've got self-attention and the feed-forward neural network. We saw that there were kind of, other than the embedding layer, there were 4 key pieces to a encoder layer. So we'll have to, figure out where those align to this picture. But at a high level, a self-attention layer is one that helps the encoder look at other words in the input sentence as it encodes a specific word. Okay, so I think that kind of makes sense. So it means if we're, encoding the word first in this sentence, then self-attention is going to take all of the other words around it and figure out how to incorporate those into the encoding of the word first. Then the outputs of the self-attention layer are fed to a feed-forward neural network, and the exact same feed-forward network is independently applied to each position. All right, so let's try and clarify here kind of the flow through the model. I think you'll come across this style of picture kind of wherever you go to learn about how Bert works. There's these kind of parallel vertical lines that run through the model architecture. And there's one for each word. I've got kind of the same thing going on in my illustrations here where we've got, each word has got a vertical line going through the 12 transformer layers. So let's talk about the actual kind of like flow of data through here to clarify what these vertical lines are referring to. Let's say we've got the sentence, I like to draw. Say, I like to draw. And we've got our CLS token and SEP. And of course, the padding tokens at the end. So with the self-attention layer, we know that all of these words are represented by embeddings. We've talked about that. So each one of these is its own little vector that's length 768. And we can say that the encoder kind of encodes one word at a time. So let's say that the current word that we're trying to encode is the word like. So the embedding for the word like is going to go into the self-attention layer. But the self-attention layer is also able to reference all of the other words in the sentence as well. Then on the output of the self-attention, we're still just encoding the word like. So we'll have some kind of output here. And this is going to be fed into the neural network layer that Jay mentioned. And then that'll produce the final encoding for the word like from this encoder. So the neural network is applied to just one word at a time, and attention is applied to one word at a time, but it's allowed to take in all the other words in the sentence to kind of inform its encoding of this word. So if we move on to the next word in the sentence, like, or excuse me, to, then it'll be the same thing. Like, I'll go in, and then only the word to will be input to the neural network, and then we'll have this encoding for the word to. All right, hopefully that helps some. We'll keep going here. Yeah, so Jay expresses that as the word in each position flows through its own path in the encoder. There are dependencies between these paths in the self-attention layer, but the feed-forward layer does not have those dependencies, and that allows us to execute the various paths in parallel. Now, I think this point about parallelization is really important. Remember that at the beginning of the tutorial, Jay said that that was a big part of what sets the transformer apart from previous approaches, is that it lends itself better to hardware acceleration. So let's look at that again. If we were to process this sentence with a traditional recurrent neural network, then we would have, let's say, we take the word I, and we've got this RNN. Okay, so at the first time step, we take the embedding for the word I, send it into the RNN. That produces some kind of hidden state information. I'll put this green box here for. And then the next word, like, will take both the embedding vector and the hidden state, and that'll produce a new hidden state. And then got the word to. So the key insight here is just that in order to process each of these words in the sentence, it has to go sequentially. You have to first process I, and then the results of that are incorporated into the processing of the word like, and then to. So it's this very sequential thing that limits the potential for parallelization. I think in Jay's wording here, says the feed-forward layer does not have those dependencies, and thus the various paths can be executed in parallel while flowing through the feed-forward layer. It doesn't look to me like there's dependencies within the self-attention layer that would prohibit encoding all of the words simultaneously, but we'll have to figure that out, I think, as we keep going here. All right, so this next piece and this next illustration here, we're just adding one small detail to the illustration. So as we encode each of these words, what we end up with is sort of a new embedding on the output of the encoder. And then for the second encoder, what gets fed into it is not the original word embeddings, but these sort of like, maybe we can call them like enriched embeddings that came from the output of the first encoder. Okay, now we get to talk about some of the sort of the high-level intuition about how self-attention works. Let's zoom in a bit here. I appreciate this this first statement here. So he kind of acknowledges that like self-attention is it sounds like it's something that's unique maybe to transformers. It's new to the transformer. So Jay explains the function of self-attention with a nice example here. The animal didn't cross the street because it was too tired. So in order to understand the word it in this sentence, the model needs to know that the word it actually refers back to this word, animal. And not only that, but it needs to know that it, does not refer to this other possible subject, the word street. So that's what self-attention does. It allows the model to associate the word it with the word animal. Now, going back to the tutorial, there's this great illustration that Jay includes that comes out of this notebook that you can look at. And let's kind of talk through what it's showing us here. So we're looking at the final layer of that six encoder stack in the original transformer. And over here, this is the word to encode currently, the word it. And over here, these are all the other words in the sentence. And, a darker color means more weight. And yeah, all of the words in the sentence are incorporated to some degree, but the most weight is on the animal. So you can see that it's kind of correctly associating those two words with it. Pretty cool. I found it to be kind of like an interesting thought experiment to try implementing, the self-attention model ourselves, or designing it basically based on what we currently know. So we know that, the objective of this function is for a given input word, score every other word by, relevance or something. Okay, so how might we do that? Well, I think the first thing that came to my mind was, what if we build this, neural network, and we could call it, like the attention scorer. And we could basically feed in the pairs of words, right? We could say like, go through every word in the sentence, can concatenate the embedding for it with the embedding for the, and feed that in to this model, and then produce some kind of score for, the relevance of the word the. Apparently it's, kind of high. And then we do the same thing for the next word in the sentence. So we'd go it and animal, and then, get another score for that pair. Apparently that's also high. I didn't leave myself much space there, did I? Let's do 0.3 and 0.3. Anyway, so you could keep doing that for every word in the input sentence. But, this wouldn't work that well because we're not taking into account the position of the words at all. So we don't know, when we're trying to score the input word the, all we know, when we're trying to score the word the, we don't know where it is in the sentence. So this model probably can't, do much. But I think it kind of makes the point, though, that somehow what we need to do is create a model that takes in the embeddings for the input words specifically, and then all of the other words in the sentence. And by looking at all of them together is able to produce a score for each word in the sentence. So let's see, how the actual solution kind of compares to this concept. Self-attention in detail. So let's first look at how to calculate self-attention using vectors, then proceed to look at how it's actually implemented using matrices. So I love that Jay includes in this post the actual matrix and vector operations that go on inside the transformer. I always feel like I need to see that in order to really feel like I understand what's happening. So I'm really glad that he gives us this detail and then also illustrates it really nicely. The first step in calculating self-attention is to create 3 vectors from each of the encoder's input vectors. So meaning like the embeddings for each word in the sentence. So for each word in the sentence, we're going to create 3 new vectors. We're going to create a query vector, a key vector, and a value vector. These vectors are created by multiplying the embedding by 3 matrices that we trained during the training process. Okay. And then we'll come back to this next paragraph in a minute here, but let's look at this, this matrix and vector math down here. So what we have is our sentence here. We're just doing a 2-word sentence to make this really simple. So this is word 1 and word 2, and the words are thinking machines. So we take those words and we look up the embeddings for them. And let's kind of ignore the machines word for a minute, just to simplify things a little bit. And let's look at just the word thinking and let's see what's going on. So we look up the embedding for the word thinking, that's this green vector, and then we multiply it by this weight matrix over here to create our query vector. And I'm sure you already know this, but just to help us visually, whenever I see an operation like this, what I do kind of mentally in my head is I say, all right, we're taking this, we're kind of rotating it 90 degrees, and we're multiplying it by this column vector here. So each element in this is multiplied by each corresponding element in this column, and then we sum those up, and that produces the value that goes right here. And then we do the same thing, take the embedding, rotate 90 degrees, multiply it element-wise against this column vector, and that produces this value. And then again for the third column. We do that with the query matrix to create the query vector, and then we've got these 2 other vectors as well. We've got the key vectors and the value vectors. So for each word, we end up with 3 vectors. All right, multiplying x1 by the wk weight matrix produces q1, the query vector. Yep, associated with that word. We end up creating a query, a key, and a value projection of each word in the input sentence. So this is a really key, a key term here, projection. What does that mean? Maybe you've seen, I'll try to give us kind of an example of of the power of projections. Maybe you've seen like the recommender system for like Netflix movie reviews. So we can take let's see, we've got Joe and Jill, and then we've got this big long vector of 10,000 movies. And we've got ones wherever there's, so those are meant to be the elements, and then, let's put a 1 in there and a 1 there. And then Jill's seen like a different set of movies. And there's a projection matrix. So this guy is 1 row by 10,000 columns. And then this guy is 10,000 rows by, let's say, 100 columns. And what we do is we multiply the set of movies that Joe's seen against this projection matrix. And what we get out is a totally different vector that is now 1 by 100. And this vector now represents Joe's taste in movies. And we would do the same thing for Jill over here. Multiply produces Jill's taste vector. And with these taste vectors, now what we can do is we can do like a nearest neighbor search. We can calculate the distance or similarity between different people's taste vectors to see which other users are most likely to share the same interests as them. And then if Jill and Joe have very similar taste, then we'll recommend a movie that Jill's seen that Joe hasn't seen, something like that. So what we've done with this projection step is we've taken a vector that was in one input space. We can call it like movies watched space. And we've projected it with this matrix, and now we're in this user taste matrix space. So we've essentially just done some linear combinations of the values in the input vector, and we've created a new vector that's somehow related to the original one, but has kind of this like entirely different interpretation. So projection is a powerful concept. You can also, you can do this the other way. You can have, these could be movies instead of users, and instead of, 10,000 movies, it could be 10,000 users. And then you can get a vector representing like the qualities of the movie, and then you can do similarity search on those movie embeddings. So there's lots of uses for projection, and that's going to be a really important part of how this is working. So what we're doing really is we're taking the embedding for thinking, and we are projecting it into the the queries space. Yeah, so there's, we're projecting the thinking embedding onto this queries space, onto the keys space, and then also onto this values space. So it's still, these three vectors are still related to the embedding for thinking in some way, but they've been transformed to a different space, a different interpretation of the input vector. Okay, let's keep going. All right, so what are the query, key, and value vectors? They're abstractions. Let me get blue back here. That are useful for calculating and thinking about attention. And what I think he means there about calling them abstractions is just that these names are a little arbitrary. The most the most correct interpretation of what's going on is really just the math. But we give the vectors these labels to kind of like keep track of what's what and help us think about what they're doing a little bit. So once you proceed with reading how attention is calculated below, you'll know pretty much all you need to know about the role each of these vectors plays. So he's just saying that once we see the math, like that's kind of all there is to know. The second step, after producing the query key and query key and value vectors in calculating self-attention, is to calculate a score. All right. Say we're calculating the self-attention for the first word in this example, thinking. All right, that means this is our input word, thinking. We need to score each word of the input sentence against this word. So if we had, a sentence with 8 words in it and the input was thinking, then we need to produce a score for the other 7 words in the sentence. In this example, it's just 2 words in the sentence. So, all right, the score determines, how much focus to place on other parts of the input sentence as we encode a word at a certain position. All right. Word at a certain position means encoding the input word. The score is calculated by taking the dot product of the query vector with the key vector of the respective word we're scoring. So if we're processing the self-attention for the word in position number 1, thinking, the first score would be the dot product of Q1 and K1. So it's interesting, we score not only the other words in the sentence, but also the input word itself. So we start by scoring Q1 times K1, and that gives us this score. And then next we take Q1 and multiply it with K2, and that gives us this score, 96. The query vector in the query space is only ever the input word. So it's always, the query vector always is specific to the word that we're currently encoding, what I'm calling the input word. So when we score the word machines, this vector Q2 is not involved. It's the query vector for thinking with the key vector for machines. Now the third and fourth steps are to divide the scores by 8, the square root of the dimension of the key vectors used in the paper, 64. This leads to having more stable gradients. There could be other possible values here, but this is the default. And then we pass the result through a softmax operation. Softmax normalizes the scores so they're all positive and add up to 1. Okay. So we're dividing by 8. 8 times 14 is 112. 8 times 12 is 96. And then we apply the softmax function. So softmax, if you remember, is e to the x over the sum of e to the x. So if you wanted to calculate the score for the word thinking, then it would be e to the 14 over e to the 14 plus e to the 12. And if you throw that in a calculator, you do get 0.88. All right, and again, the purpose of softmax always, it guarantees that that all of the numbers will add up to 1. So it gives us these kind of proportions. The softmax score determines how much each word will be expressed at this position. Interesting. So it's kind of like, I'm gonna say that this is like the the relevance of each word in the sentence to the current input word. And yeah, and we will see that these scores get multiplied against the value vector, and then we combine the value vectors. So it is sort of it's definitely like a weighting. Clearly, the word at this position will have the highest softmax score. Now, this is something I've got to figure out. I don't understand why that's the case. I guess in order for this one to have the highest score generally, then what would that mean? That would mean that the query and key vectors for a given, for any word, I guess, are very similar, and so they have a high dot product. Why the query and key vectors would be similar for a word, I don't know that. So it's not clear to me how Jay is drawing that conclusion here. So open question. All right. Fifth step is to multiply each value vector by the softmax score. Multiply the value vector, that's this guy, the V, by the softmax score, in preparation to sum them up. The intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words by multiplying them by tiny numbers like 0.001, for example. Right, so we're weighting the different words in the sentence. The sixth step is to sum up the weighted value vectors. This produces the output of the self-attention layer at this position. So, input for input word thinking, look up its embedding, compute the query key and value vectors for thinking, multiply query 1 with key 1, get a score, multiply query 1 with key 2, get a score, and now we're going to multiply these scores against each position of the value vector. And then we'll sum those together to create this final z vector. And then if I'm understanding his illustration correctly, the way z2 would be calculated is to then kind of move this box over, right? And this time, machines would be the input word. And we would do query 2 against key 1 and query 2 against key 2. And then that would produce this output vector. Okay. That concludes the self-attention calculation. The resulting vector is one we can send along to the feed-forward neural network. In the actual implementation, however, this calculation is done in matrix form for faster processing. So let's look at that now that we've seen the intuition of the calculation on the word level. So yeah, essentially we're going to go through this same process, except it's actually possible to combine these steps and combine the inputs into matrices. So the matrix calculation of self-attention. First step is to calculate the query key and value matrices. We do that by packing our embeddings into a matrix X and multiplying it by the weight matrices we've trained. Okay, so the weight matrices stay the same, but the embedding, instead of an embedding vector, we now have an embedding matrix. So each row of the matrix corresponds to a different word. In this case, thinking and machines. And same intuition here applies. So we take this vector, multiply it against this column, and that produces this value. And we take that vector, multiply it against this column, that produces this value. Okay, and then now we do the same thing for machines. Multiply that against that. That produces this value. Multiply against that. Produces that value. All right, you get the picture. You know how matrix multiplication works. So we've got 2 by 512 times 512 by 64. And whenever you do matrix multiplication, these two numbers need to match, and you drop them and take the outer dimensions. So that leaves us with a 2 by 64 matrix, which is this guy. And again, this corresponds to thinking and this one to machines. So we do that for all three of these spaces, the query space, the key space, and the value space. And we're just doing it for all of the input word embeddings all at once. And that's because the reason we do that is that GPUs and CPUs as well are much more efficient when doing matrix multiplication as opposed to a vector matrix multiplication. And the reason for that is it's got additional hardware that allows it to kind of reuse this matrix in in memory and be processing, both input vectors at the same time, because those two operations are, mathematically independent. Okay. Finally, since we're dealing with matrices, we can condense steps 2 through 6 in one formula to calculate the outputs of the self-attention layer. Now, I tried going through Jay's condensed illustration here, but it just didn't work for me. I needed expanded a little bit more. So let's kind of talk through the steps a little more carefully. Now, he does say that this equation here condenses steps 2 through 6. So that leaves out step 1. And step 1 was to perform the projections. So we took the embeddings, the word embeddings in X, and multiplied it against each of the 3 weight matrices, and that created our Q, K, and V matrices. Now, steps 2 through 4 dealt with the scoring. So let's break those down. And let me actually scoot these over a little bit so we can. So just like the picture over here, we're going to multiply Q and K. And let's look at the dimensions just so we've got the right picture. 2 rows, 64 features each. And then same dimensions, just transposed. So 64 by 2. And if we take the product between those 2 matrices, then we eliminate the inner dimensions, and we're left with this 2 by 2 matrix of scores. Okay, we divide all the scores by the value 8. That's kind of a simple step. And then the softmax is always done on a list of values. So here we're going to do the softmax on the rows of this matrix. So really it's, softmax of this row and softmax of this row. So all that does, is it gives us the same 2 by 2 matrix, but now each row sums to 1. So this score matrix, isn't in the picture up here, and I think that kind of made things just a little too confusing for me. So let's move down now to steps 5 through 6, and it looks like I need a little more space. So let's see if we can okay, I created a little more space for us, so let's get back to this. So we're going to put this new scores matrix down here. And this is steps 5 to 6, which is the weighted sum of the value vectors. So we got our score matrix. We're going to do multiplication here. And that's going to yield our Z matrix. So scores is always going to be square, and the dimension is the number of words in the sentence. In this case, just 2. And then over here we've got 2 by 64. So the way this actually plays out is the scores in this row will be used to calculate this row of the Z matrix. And the way that happens is, maybe we can pick like 2 colors here. Maybe we'll do we'll say that one. We multiply that against each of these. And then we multiply that against each of those. And we sum those up to create these values. So row 1 of Z was created by multiplying row 1 of the scores matrix with the value vectors. Cool. So at this point, I feel like I've got a pretty good handle on how those z vectors are calculated. But let's remind ourselves like what those actually are. What do the z vectors represent? So going back to Jay's post earlier on, kind of in the more of the architecture drawings, we saw this illustration. So the input words and their embeddings go into the self-attention layer, and then the output of the self-attention layer is these z vectors that we've been looking at. And then those get passed into this feed-forward network. So what we're going to be looking at in the next video is multi-headed attention. And multi-headed attention is going to explain a few things that we've kind of ignored so far. It's going to explain, why we need this neural network. And then it's also going to explain why the key query key and value vectors are 64 features and not 512. So those two things will make sense once we talk about multi-headed attention. It's not that difficult of a concept. It's really just like we're applying this self-attention concept multiple times, allowing the different attention heads to kind of be looking at different things. So we'll get to that in the next video. But before we conclude this video, I think we can try to get a little bit more intuition about what's going on in this self-attention layer. Okay, so back to this illustration of the attention head and what it's looking at in the sentence. So again, this is our input word, and then these are the all the words in the sentence and the score that each one's getting. And the and animal are getting high scores. So how did we calculate the score for these two words? So we take the query vector for it, and we take the dot product between that and the key vector for animal. And then, there was that step of dividing the result by 8 as well as applying the softmax. But really, for the score to be high, so if the score for animal is high, then what? Like what would have to be true in order for the score to be high? Well, the dot product has to be large, right? So let's look at what the dot product actually is and see if we can kind of like infer anything about the nature of these vectors from the definition. The dot product between two vectors A and B is given by the magnitude of A times the magnitude of B times the cosine of the angle between them. And the cosine, let's look at some cosine values. So if two vectors are pointed in the same direction, then the angle between them is 0 degrees, and the cosine of 0 degrees is 1.0. If they are orthogonal to each other, the angle is 90 degrees, then the cosine is 0.0. And then if they point in opposite directions, then the cosine is negative 1.0. So what this tells us is that one way to make the dot product larger is for both vectors to point in the same direction. And then, of course, the other way to make the dot product large is just for either of the magnitudes to be large. So it's kind of inconvenient to me in the interpretation that, like option number 2 here is complicating. Option number 1, though, I feel like there's some intuition to this. So if 2 vectors point in the same direction, then it tends to mean that they represent something similar, right? We take the cosine of their angle. That's the cosine similarity. So if 2 vectors are similar, then the cosine between them should be a higher number, closer to 1.0. So that tells us that for the score to be high for it and animal, these 2 vectors must be similar. And again, the other way is if the magnitude of one of these vectors is just really high, but that provides less intuition. So I hope that that's not really the reason that these words get scored high. I hope it's because the query and key vectors are similar. Cool. So, I think we've covered one of the most important pieces of the inside of the transformer here. We still have some more content to go, but I don't know. I'm really excited that we made it this far, and I'm proud of our, what we've accomplished here. Thanks, guys.